Every takeoff is a race against distance. Engines roar, the runway rushes beneath, and the aircraft gathers the strength to lift. But when that strength comes too late, there is nowhere left to go. In this video, we look at the real moments when runways were too short, when a single second or a single mistake changed everything. If you want to see more true stories that shaped aviation safety, make sure to subscribe and like the video. It helps us keep telling the stories behind the skies. January 13th, 1982. Washington, D.C. was frozen under one of the worst winter storms in years. Snow blanketed the city, the Potomac River was crusted with ice, and the runways at National Airport were covered in slush and freezing mist. Despite the chaos, Air Florida Flight 90 prepared for departure, a short hop to Fort Lauderdale, Florida. The aircraft was a Boeing 737 crewed by Captain Larry Wheaton and First Officer Roger Pettit. Both men were experienced, confident, and determined to leave before the next wave of weather shut the airport down. But as the snow kept falling, the decisions made in those minutes on the ground would seal their fate. The plane was de-iced once, but the delay in departure allowed snow and slush to build back up on the wings. The crew, trying to follow ground control instructions, taxied behind another jet to the runway. What they didn't realize was that the hot exhaust from that aircraft was blowing partially melted slush and de-icing fluid back onto their own wings and sensors, refreezing almost instantly. At 3:41 in the afternoon, Flight 90 began its takeoff roll on runway 36. The engines roared, but something was wrong. The thrust indicators showed lower than normal power, and the acceleration felt sluggish. The first officer expressed concern, but the captain, convinced the readings were inaccurate because of ice buildup on the sensors, decided to continue the takeoff. As the aircraft climbed to just a few hundred feet, it began to shake. The stall warning horn sounded, but by then, there was no room left to recover. The Boeing lurched, rolled, and struck the bridge, spanning the Potomac River, tearing through traffic before plunging into the icy water below. 78 people were killed, including 4 motorists on the bridge. Only 5 passengers survived, clinging to wreckage in the freezing current as bystanders on the shore fought to reach them. Television cameras captured the rescue in real time, a haunting image of survival in the middle of the nation's capital. The NTSB's investigation revealed a deadly chain of small decisions. The engines had been producing only about 80% of the required thrust because ice had clogged the engine pressure ratio, EPR sensors. The pilots had also failed to activate engine anti-ice systems, believing that their use would reduce takeoff power. Most critically, they had not recognized how ice contamination on the wings destroyed the aircraft's ability to generate lift. The report concluded that the probable cause was the crew's failure to use proper de-icing and anti-icing procedures, combined with their decision to take off with visible snow and ice accumulation on the airframe. In the aftermath, regulators and airlines rewrote procedures for cold weather operations. Crews were trained to perform visual contamination checks before takeoff, regardless of instrument readings. Anti-ice systems were to be engaged early and left on throughout taxi and takeoff in freezing conditions. Ground crews were retrained to understand that one round of de-icing fluid wasn't always enough. The accident also reshaped how cockpit communication was taught. In simulator training, pilots began practicing assertive intervention. The idea that the first officer has not just the right, but the duty to challenge unsafe decisions. It was one of the key steps that led to modern crew resource management. Today, every winter departure from a snowy airport carries the invisible legacy of Flight 90. When you hear a pilot call for de-icing, when you see trucks spraying fluid across a frozen wing, or when takeoff is delayed for one more inspection, those precautions trace back to the lessons written on that frozen January day. Air Florida Flight 90 became more than just an accident. It became a reminder that even in the most advanced machines, nature always holds the final say. And in the battle between ice and lift, hesitation lasts only a second, but its consequences can last forever. It was the 27th of December, 1991. Sweden was wrapped in deep winter cold. Snow covered the forests, and the air was thick with freezing mist as Scandinavian Airlines Flight 751 prepared for departure from Stockholm's Arlanda Airport. The aircraft, a McDonnell Douglas MD-81, carried 129 people bound for Copenhagen. The flight seemed routine, calm, almost peaceful. But in reality, the seeds of disaster had already formed long before takeoff. During the night, the plane had been parked on the ramp through freezing rain and sleet. Thin sheets of ice had built up on the wings, invisible beneath a layer of frost. When the ground crew sprayed de-icing fluid before departure, they cleared the visible ice, but not the frozen layer hidden deeper near the wing roots. No one knew that inside the engines, small chunks of this ice were waiting to break loose. As the aircraft accelerated down the runway, Captain Stefan Rasmussen and First Officer Ulf Kedermark noticed nothing unusual. The MD-81 lifted smoothly into the grey winter sky. Just 90 seconds later, the first engine began to surge. Then the second followed. Inside both Pratt and Whitney T8D engines, ice broke free from the wings and was sucked into the compressors, shattering fan blades and igniting a chain reaction of destruction. Within seconds, both engines flamed out completely. The cockpit filled with alarms. The noise of the engines vanished. The aircraft was now a powerless glider at 3,000 feet in freezing air. There was no time to restart. The crew declared an emergency and began searching desperately for a place to land. Below them was a dense forest, blanketed in snow, dotted with farmhouses and roads. Captain Rasmussen guided the plane toward an open field near the small village of Gottröra. The MD-81 descended silently, wings level, as the pilots used every ounce of skill and instinct to keep the nose from dropping. They extended the flaps to slow down and aimed for the narrow clearing ahead. Just seconds before impact, the tail struck a tree, tearing off part of the fuselage. Then the aircraft slammed into the snow-covered ground and split into 3 large sections. Miraculously, all 129 people survived. Only a handful suffered serious injuries. Villagers rushed from nearby homes through knee-deep snow to help passengers escape the wreckage as the plane settled into the frozen field like a broken bird. The investigation by the Swedish Accident Investigation Board revealed a complex failure chain. The engines had no ice protection system capable of preventing large chunks of clear ice from breaking free. The pilots were never informed that the MD-80 series was vulnerable to this type of ice ingestion during climb. The de-icing procedures at the airport also failed to address the possibility of ice refreezing near the wing route, but the report also highlighted extraordinary airmanship. Captain Rasmussen's decision to maintain airspeed, keep wings level, and use the field instead of attempting a turn saved every life on board. His calm technical control under impossible pressure became one of the most studied examples of successful emergency handling in aviation training. In the years after the crash, aircraft manufacturers modified engine nacelles and ice detection systems to prevent such failures. Airlines around the world introduced stricter pre-flight inspections in icing conditions, focusing on hidden ice accumulation. Today, SAS Flight 751 is remembered as one of the most remarkable survival stories in modern aviation. It proved that even when technology fails completely, human skill and composure can still make the difference between tragedy and miracle. It was a quiet summer morning on August 22nd, 1985, at Manchester International Airport in England. Holidaymakers filled the terminal, laughing, chatting, and taking photos as they prepared to escape to the Mediterranean sun. Among them were 55 passengers and 8 crew members boarding British Airtours Flight 28M, a Boeing 737 bound for Corfu. The weather was clear, the visibility perfect, and there was nothing to suggest that this short flight would become one of the most defining moments in modern aviation safety. At 7:13 in the morning, the aircraft began its takeoff roll along runway 24. In the cockpit were Captain Peter Terrington and First Officer Brian Love, both experienced pilots who had flown this route many times before. The takeoff appeared normal. The engines roared, the aircraft accelerated steadily, and the passengers in the cabin leaned back in their seats, ready for the familiar lift of flight. But then, just seconds before reaching rotation speed, a loud bang echoed through the cabin. Passengers on the left side saw flashes of orange light through the windows. In the cockpit, the pilots felt a violent shudder. Warning lights illuminated. The left engine had suffered a catastrophic failure. A compressor blade had fractured, puncturing a fuel line and igniting a massive external fire. Captain Terrington instantly aborted the takeoff, pulling the throttles back and applying maximum braking. The Boeing came to a halt within seconds, veering slightly off the runway's centerline. But the danger was only beginning. Flames from the ruptured fuel line poured back along the left wing, heating the aluminum skin until it began to melt. Burning fuel penetrated the cabin through broken seals and side panels. Inside, thick black smoke began to fill the cabin almost immediately. Passengers coughed and screamed as visibility dropped to 0 within seconds. Flight attendants rushed to open the exits, but one of the overwing exits jammed due to the intense heat. The aisle became a bottleneck of confusion and panic. The fire was so close to the fuselage that within 90 seconds, the cabin temperature reached levels that made survival nearly impossible. Yet the rescue teams were already racing across the tarmac. Airport fire trucks arrived less than 2 minutes after the abort, blasting foam over the fuselage and wing. Firefighters pulled survivors from the right side exits, guiding them away from the wreckage as smoke billowed hundreds of feet into the sky. Despite their efforts, 55 people lost their lives, not from burns, but from smoke inhalation and toxic fumes. Most of them were seated near the rear of the aircraft, where the thickest smoke collected. The tragedy was devastating, but it also led to one of the most significant safety revolutions in aviation history. The Air Accidents Investigation Branch AAIB report revealed that the engine failure alone should not have caused such a high fatality rate. The true killers were toxic materials used inside the cabin, narrow exit access, and a lack of clear evacuation procedures. The investigators found that seat fabrics, wall panels, and overhead bins produced lethal gases when exposed to heat. The aisle spacing near the overwing exits was too narrow, preventing rapid movement. Some passengers froze in place due to smoke disorientation, a phenomenon known as post-impact paralysis. The recommendations that followed transformed aircraft design and passenger safety worldwide. Cabin interiors were completely redesigned with low-toxicity, fire-resistant materials. Exit signs were made larger and illuminated even in heavy smoke. Floor lighting was added to guide passengers toward exits in total darkness. The 90-second rule was formalized, requiring all commercial aircraft to demonstrate that a full evacuation could be completed in a minute and a half, using only half the available exits. British Airtours Flight 2. 8M also reshaped the culture of crew training. Flight attendants began receiving enhanced instruction in smoke management, rapid assessment, and crowd control during emergencies. Pilots were trained to consider the possibility of abort side wind direction before stopping the aircraft, minimizing the chance of fire spreading to the fuselage. For the families who lost loved ones that morning, none of these reforms could bring back what was taken. But their voices, along with those of the survivors, ensured that no one would ever again underestimate the danger of post-crash fires. Every illuminated floor path you see on an airplane today, every fire-resistant seat cushion, every calm but firm voice you hear in an emergency briefing, all of it carries the legacy of Manchester, 1985. August 3rd, 2016. The heat over Dubai shimmered like glass. Emirates Flight 521, a Boeing 777, was completing its journey from Thiruvananthapuram, India, carrying 282 passengers and 18 crew members. The approach seemed normal. Winds were strong but within limits, and the skies were hazy with desert humidity, a typical late summer morning in the Gulf. In the cockpit were Captain Hassan Al-Hamadi and First Officer Jeremy Webb. Both pilots were highly experienced, having completed hundreds of approaches to Dubai's long runways. But that morning, the challenge wasn't the weather or the workload, it was timing. As Flight 521 neared the runway, a wind shear warning sounded. The aircraft began to lose lift just seconds before touchdown. Following procedure, the pilots decided to perform a go-around, a standard maneuver to climb away and try the approach again. But in the split-second confusion of automation and instinct, something went terribly wrong. Instead of advancing the throttles manually to full power, the crew relied on the auto-throttle system to respond automatically. However, after touchdown, the auto-throttle was no longer active, a nuance of Boeing logic that requires manual reactivation after weight-on-wheels contact. The throttles remained idle. The aircraft lifted briefly, but with no thrust, its speed bled away. The massive jet hung in the air for only a few seconds before sinking back toward the runway. The right landing gear collapsed, then the left. The fuselage slammed onto the tarmac and slid more than 800 meters before coming to rest in a cloud of dust and smoke. In the cabin, panic broke out. Overhead bins flew open as oxygen masks and insulation panels dropped from the ceiling. Passengers could smell burning metal and aviation fuel. Within seconds, flames erupted from the right engine, spreading rapidly along the wing route. Inside the cockpit, the pilots issued a mayday call while trying to shut down the engines and deploy the fire handles. Cabin crew began shouting commands, urging passengers to evacuate. Some ignored instructions and tried to grab luggage, blocking aisles and slowing the escape. Outside, rescue vehicles raced toward the crippled jet, foam cannons already firing as black smoke billowed over the runway. Miraculously, all 300 people on board escaped the aircraft before it exploded. Moments after the last person exited, a massive fireball consumed the fuselage, captured in shocking clarity by cell phone cameras and security footage. Tragically, one firefighter lost his life battling the blaze. The investigation by the United Arab Emirates General Civil Aviation Authority revealed a complex chain of technical logic, human reaction, and procedural timing. The flight crew had followed most standard procedures, but misunderstood how the aircraft's automation interacted with the go-around command after touchdown. When the throttles were not advanced manually, the aircraft lacked the thrust needed to climb. This accident became a landmark study in what aviation experts call automation expectation. Modern aircraft are designed to reduce pilot workload, but they also create new layers of dependency. In this case, the pilots expected the system to act, but it didn't. The GCAA's final report led to major reforms in go-around training worldwide. Boeing updated manuals and simulator scenarios to emphasize manual throttle control during rejected landings. Airlines introduced refresher training on automation modes and human decision-making under stress. The concept of go-around commitment, the exact moment a pilot must choose between continuing to land or climbing away, became a renewed focus in safety programs. What made Emirates Flight 521 remarkable was not only the chain of small mistakes but the outcome. Despite a catastrophic impact and fire, almost every life on board was saved. That survival was the result of disciplined cabin crew performance and rapid emergency response. The professionalism of the flight attendants, who guided passengers through smoke and flames in under 2 minutes, became a model for future evacuation training. Today, the burned remains of Flight 521 stand as a haunting reminder that even the most advanced systems cannot replace human awareness. It taught aviation another hard truth. Sometimes the difference between a near miss and a disaster is not technology, but understanding it. The flames on the runway in Dubai faded long ago, but the lesson remains carved into aviation history, that in the final seconds before impact, clarity of action matters more than any checklist or machine. It was the morning of August 31st, 1988, at Dallas-Fort Worth International Airport. Delta Airlines Flight 1141, a Boeing 737, was preparing for a short flight to Salt Lake City with 108 people on board. The weather was warm, the sky clear, and the mood inside the cabin was calm. Business travelers read newspapers, families buckled seatbelts, and the crew prepared for what should have been an uneventful departure. In the cockpit sat Captain Larry Davis, First Officer Kerry Kirkland, and a flight engineer on the jump seat, an observer from another crew. The pilots were relaxed, chatting about company changes, personal matters, and even joking as they went through the pre-flight process. The aircraft pushed back, taxied toward runway 18 left, and lined up for takeoff. What no one in the cabin knew was that a single, crucial step in the checklist had been skipped. The Boeing's leading-edge slats and trailing-edge flaps, the devices that help the wing generate lift at low speeds, had not been extended. Without them, the aircraft's wings would not produce enough lift during takeoff. It was a step so fundamental that it was included in every pre-takeoff checklist, repeated twice, and cross-verified by both pilots. But that morning, in the relaxed rhythm of casual conversation and cockpit banter, it never happened. At 8:59 a.m., the aircraft began its takeoff roll. The engines roared as the jet accelerated down the runway, reaching 160 knots. Captain Davis pulled back on the control column. The nose rose, but the plane refused to climb. The stick shaker rattled violently, warning of an imminent stall. Within seconds, the left wing dropped sharply, and the aircraft crashed just beyond the end of the runway, bursting into flames as it skidded across the grassy field. Fire and smoke filled the fuselage. Passengers screamed as flight attendants struggled to open emergency exits. Some exits jammed. Others opened partially. Flames spread quickly along the left side, but many passengers managed to escape through the right overwing exits and emergency slides. When rescue crews arrived, they found a horrific scene. A burning fuselage split open, with survivors staggering away from the wreckage. 14 people lost their lives, including 2 crew members, but 64 survived, many with burns and injuries. The investigation by the National Transportation Safety Board would expose not just one missed action, but a systemic problem inside the cockpit culture of the time. Flight recorders revealed that the crew had spent much of the taxi out engaged in casual, non-essential conversation, discussing flight attendants, company rumors, and personal stories, in clear violation of the sterile cockpit rule, which prohibits unrelated talk during critical phases of flight. Because of this distraction, they failed to notice that the flap lever was still in the up position. To make matters worse, the takeoff warning system, designed to alert pilots when flaps or slats were not set, failed to activate due to a maintenance fault. It was the perfect alignment of human complacency and technical oversight. The NTSB's final report was damning. It concluded that the probable cause was the flight crew's failure to extend flaps and slats before takeoff, compounded by the lack of discipline and professionalism in the cockpit. The investigators highlighted how informal cockpit behavior, once seen as harmless, could erode the safety margins that aviation depends on. As a result of Flight 1141, airlines around the world began reinforcing strict cockpit communication protocols. Crew resource management, CRM, training was redesigned to emphasize respect for checklist discipline and sterile cockpit procedures. Flight deck recorders became more closely reviewed during training evaluations to ensure that crews maintained focus during taxi and takeoff. Delta, in particular, changed its entire training philosophy, making checklist verification a sacred process. The accident became one of the most cited examples in pilot training programs, a reminder that professionalism in the cockpit is not about experience or confidence, but consistency. Every time a pilot now reads back "flaps set" or "slats extended," that simple phrase echoes back to Dallas-Fort Worth, 1988. It is a ritual born from the memory of those who never made it past the end of the runway. Flight 11, 41 taught aviation that disasters are rarely the result of one big failure. They are built, quietly, in moments of distraction, in seconds of overconfidence, in the absence of a single line on a checklist. It was the evening of December 8th, 2005. The holiday season had already settled over Chicago. Snow fell thick and heavy, blanketing the city in white. At Midway International Airport, one of the country's busiest urban airfields, visibility was dropping fast. The runways were slick with ice. The wind howled across the tarmac, and plows struggled to keep up with the accumulating snow. Southwest Airlines Flight 12. 48, a Boeing 737 arriving from Baltimore, was on final approach. There were 100 passengers and 5 crew members on board, families returning home, business travelers, and flight attendants who had done this route countless times before. The mood inside the cabin was calm. Passengers could see the faint glow of the city through the snowstorm, unaware that the next few minutes would test every assumption about short runway operations and winter landings. In the cockpit sat Captain Brian Nunn and First Officer Stephen Oliver. Both were experienced, but conditions that night were unforgiving. Winds were gusting, visibility was less than 1 mile, and the temperature hovered just below freezing. Chicago Midway, unlike major international airports, has limited runway length, just under 6,000 feet, surrounded on all sides by city streets, homes, and buildings. There is no open field at the end. Every foot of asphalt matters. As the 737 descended through the clouds, the crew reviewed their landing data. They selected flaps 40 and armed the auto brake system to level 2, a moderate braking setting. They also activated reverse thrust logic for additional stopping power. But what neither pilot fully accounted for was the combined effect of snow contamination and a shifting tailwind on the landing distance. At 7:14 p.m., the aircraft touched down on runway 31 center, about 1,000 feet past the threshold. To most passengers, the landing felt firm but normal. Then the reverse thrusters deployed. But the airplane didn't slow. The wheels spun in the slush, unable to grip the icy surface. The autobrake system applied maximum pressure, but friction was almost non-existent. Inside the cockpit, the pilots realized they were running out of runway. Captain Nunn pulled the manual brake levers, but the 737 continued to slide. "We're not stopping," one of them said. Outside, the end of the runway and the airport fence rushed closer through the snow. With only seconds left, the aircraft skidded off the runway, plowed through the perimeter fence, crossed a busy intersection, and crashed into 2 cars on Central Avenue before coming to rest against a road barrier. Flames erupted briefly from a damaged engine, and emergency vehicles raced to the scene. Inside the cabin, passengers were thrown forward, but largely unharmed. The flight attendants acted instantly, commanding everyone to unbuckle and evacuate. Within a minute, all 103 people were outside in the snow, huddled together under flashing red and blue lights. Tragically, 1 child on the ground was killed when the aircraft struck a passing car. The investigation by the National Transportation Safety Board painted a detailed picture of how a normal landing turned into disaster. The key finding was that the pilots had not properly adjusted their landing distance calculations for the rapidly changing conditions. The tailwind, which increased just before touchdown, effectively extended the aircraft's stopping distance by hundreds of feet. Combined with the snow and the delayed deployment of thrust reversers, the plane simply ran out of space. The auto-brake system, designed to assist but not replace pilot judgment, was set too low for the runway condition. The thrust reversers, which provide critical deceleration on slippery surfaces, had been briefly inhibited by the system logic because the plane's weight-on-wheel sensors detected inconsistent data during touchdown. The NTSB also noted a deeper issue: operational pressure. Midway is a challenging airport for large aircraft, and landing there in winter requires quick decision-making. Southwest's company culture emphasized maintaining schedule reliability, which may have influenced the decision to continue the approach instead of diverting to a longer, safer runway at Chicago O'Hare. As a result of the accident, Southwest Airlines and the FAA introduced new landing performance tools that automatically calculate braking distance using real-time runway condition reports, tailwind data, and aircraft weight. The FAA also required all airlines to adopt stricter runway overrun prevention programs. Midway itself was later equipped with an engineered materials arrestor system, EMAS, a special bed of crushable concrete at the runway ends that can safely stop an aircraft if it overruns. The crash of Flight 1248 became a case study in how winter weather can quietly erase even the best laid plans. It showed that no checklist or automation can replace human caution, that sometimes the safest decision is not to land at all. Today, every pilot landing on a short, snow-covered runway runs the same calculations that Captain Nunn once faced. But now, they do it with better data, better tools, and a clearer understanding of what's at stake. For the families who remember that cold night in Chicago, the lessons written in snow and fire continue to echo through every landing checklist and every cautious go-around. Because in aviation, the difference between safe and sorry often lies in a few hundred feet of frozen concrete. July 25, 2000, Paris, Charles de Gaulle Airport. The runway shimmered under the summer heat as one of the most iconic aircraft in history prepared for takeoff, the Air France Concorde. Flight 4. 590 was bound for New York's John F. Kennedy Airport, carrying 100 passengers, 9 crew members, and the weight of technological pride. The world's only supersonic passenger jet stood poised, sleek and white, its delta wings cutting the sky like a blade. For decades, Concorde had represented perfection. It flew higher, faster, and more elegantly than any other aircraft ever built. But on that day, its final flight would prove that even perfection can be undone by something as small as a piece of metal on a runway. At 4:42 p.m., Captain Christian Marty, a veteran pilot and former French Air Force member, lined up on runway 26 right. The aircraft's Olympus engines roared to life, their deafening thrust pushing the needle toward takeoff speed. Acceleration felt brutal, raw, as always with Concorde. Yet, in the middle of that power, destiny waited in the shape of a small titanium strip lying unnoticed on the runway. Moments earlier, a Continental Airlines DC-10 had taken off from the same strip. During its roll, a piece of metal from its engine thrust reverser had detached and fallen onto the tarmac. No one had seen it. No warning was issued. And now, the Concorde's left main landing gear was speeding directly toward it. At 175 knots, the tire struck the strip. Instantly, the rubber exploded. A section of the tire, weighing several kilograms, shot upward like a bullet. It slammed into the underside of the left wing, puncturing the fuel tank. In seconds, a jet of fuel began spraying back under immense pressure, and a spark ignited it. A passenger in the terminal later described seeing a streak of flame trailing behind the aircraft as it roared past. Inside the cockpit, alarms began flashing. Engine 2 lost power. Then, Engine 1. The crew struggled to maintain control, but thrust was uneven, drag was increasing, and the aircraft was no longer accelerating. They were already committed. Aborting takeoff at that speed was impossible. Concorde lifted off, but just barely. Flames trailed from its wing as it climbed sluggishly over the rooftops of Gonesse, a suburb near the airport. The co-pilot radioed, "We have a fire on engine 2. Request emergency landing." But it was too late. With both left engines failing and the wing structure weakening, the aircraft lost lift. It rolled left and slammed into a small hotel and restaurant, erupting into a massive fireball. 109 people, all passengers and crew, were killed, along with 4 people on the ground. It was over in less than 2 minutes. The world watched in disbelief. The aircraft, once seen as a symbol of progress and perfection, had fallen to the ground because of a piece of debris smaller than a ruler. The investigation that followed, led by the French BEA, was one of the most detailed in aviation history. It revealed not only how the titanium strip had caused the disaster, but how multiple small failures in oversight, communication, and design had aligned with devastating precision. The report concluded that the bursting tire caused a shockwave that ruptured the fuel tank. The tank had no protective liner, a design vulnerability known since the 1970s, but never fully addressed. Engineers had believed the chances of such a puncture were nearly impossible. They were wrong. After the accident, the entire Concorde fleet was grounded. Engineers developed Kevlar liners for the fuel tanks, redesigned the tires with new materials to resist fragmentation, and added electrical shielding to prevent ignition. Runway inspection procedures were overhauled across the world, with new debris detection technologies introduced. The smallest fragments on a runway would now be taken seriously. But despite these changes, Concorde would never recover its glory. The magic was gone, replaced by caution and fear. The aircraft returned to service briefly in 2001, but the events of September 11th and rising operational costs sealed its fate. By 2003, the era of supersonic passenger flight had ended. Captain Marty's final flight became an inflection point in aviation history, a moment where technology's pride met the reality of imperfection. It showed that even at the highest levels of engineering, safety is not about how advanced a machine is, but how small its weakest point can be. Today, pieces of Concorde are displayed in museums, polished, revered, and silent. Yet the photographs of that day, the fire trailing behind the wings of the world's most beautiful jet, remind us of a simple truth. In aviation, nothing is too small to matter. It was August 20th, 2008, a blazing summer afternoon in Madrid. Temperatures on the tarmac reached 40 degrees Celsius, and the heat shimmered over the runway like liquid glass. At Barajas Airport, Spanair Flight 5022, a McDonnell Douglas MD-82, prepared for its short journey to Las Palmas in the Canary Islands. There were 172 people on board, families, vacationers, crew members, most eager to leave the heat of Madrid behind for the cool Atlantic breeze. To the passengers, the scene looked normal. Flight attendants smiled, children pressed their faces against the windows, and the familiar rumble of jet engines filled the cabin. But behind the calm exterior, a chain of small technical faults and human assumptions was quietly tightening. The kind of chain that would, in just minutes, take the lives of 154 people. The aircraft's captain, Antonio Garcia Luna, and First Officer Francisco Muley were both experienced pilots. Earlier that day, their first attempt to depart had been aborted due to a small fault, an air temperature probe reading incorrectly. The maintenance crew had addressed the issue by deactivating the heater system for the probe, a standard temporary fix allowed by Spanair's minimum equipment list. The crew returned to the gate, paperwork was completed, and clearance for departure was granted again. Everything appeared routine. But inside that long list of checklists and resets, something subtle had been lost. As the aircraft taxied back to runway 36 left, the cockpit grew warm. The pilots reviewed their pre-takeoff items, but the mood, captured later on the cockpit voice recorder, was weary and distracted. They had already been delayed for more than 2 hours. The heat was oppressive. The MD-82's cockpit ventilation was minimal when idling on the ground, and sweat rolled down their necks as they worked through the lists. They reached the flaps and slats item, a critical setting that extends panels on the wings to generate lift at low speeds. But this time, the item was skipped. The switch remained in the up position. The oversight was almost invisible. A single step missed among dozens. At 2:24 p.m., Spanair 5022 began its takeoff roll. The engines roared to full power, and the MD-82 accelerated rapidly down the runway. But as the airspeed climbed, something was wrong. The plane felt heavy, sluggish, glued to the ground. The pilots pulled back on the yoke, expecting the nose to rise. It didn't. The stick shaker activated, a stall warning. The aircraft barely left the runway before slamming back down, veering left, and exploding into a ball of fire beyond the perimeter fence. Thick black smoke rose over the Spanish capital. Rescue crews raced toward the flames, but the heat was overwhelming. Only 18 people survived. When investigators from the Spanish Accident Board, CIAIAC, arrived at the crash site, they found a scene of utter destruction. Yet the recorders survived, and the story they told was painfully familiar to those who remembered Delta Airlines Flight 1141 or Northwest Flight 255. The takeoff configuration was wrong. The flaps and slats, essential for generating lift, were never deployed, and the aircraft's takeoff warning system, designed to alert the pilots to such a mistake, never sounded. The reason, investigators discovered, was chillingly simple. During the maintenance work earlier that day, a circuit breaker for the air temperature probe heater had been pulled. That same circuit also powered the takeoff configuration warning system. When the technicians reactivated the aircraft, they never reset the breaker. The system that should have screamed "no takeoff" remained silent. The investigation revealed a web of human and procedural errors. The pilots missed the flap setting in their checklist verification. The maintenance crew failed to recognize the circuit's link to the warning system. The airline's internal processes allowed such a maintenance sign-off to proceed without additional cross-check. And on top of all of it, fatigue and time pressure dulled the crew's vigilance. The report's findings were damning. This was not just a pilot error, but a systemic failure of oversight. The final seconds of the cockpit voice recording captured the confusion as the stick shaker rattled, the engine strained, and the ground approached. They never knew why the plane wasn't lifting. They never heard the warning they were trained to expect. Following the tragedy, Spanair and European regulators implemented sweeping changes to maintenance verification and flight deck warning systems. Airlines across the world reviewed their wiring diagrams to ensure that safety-critical systems could never share a circuit with unrelated components. The MD-80 series, already aging, received additional modifications to prevent this design vulnerability from ever causing another disaster. The accident also reignited discussions about human factors, how pilots under stress, heat, and delay are more likely to miss checklist items. Crew resource management training began emphasizing the need for strict verbal cross-confirmation, even in the most routine situations. For Spain, it was a national tragedy. For aviation, it was another lesson written in heartbreak. Today, the site of the Spanair crash near Madrid's Barajas airport, is marked by a simple memorial. 154 stones arranged in a circle, each bearing the name of a life lost that day. When the sun sets, their shadows stretch across the grass, silent reminders that in aviation, every switch, every circuit, every checklist line is sacred. Every takeoff is a promise, a moment when hundreds of tons of metal, fuel, and hope surge forward together, chasing lift against the limits of gravity. It is one of the purest acts of trust in modern life. Yet every pilot knows deep down that there comes a point when there's no more runway left. A point where commitment replaces caution, and every decision made in the previous seconds determines what happens next. The stories you've heard of ice-covered wings, skipped checklists, malfunctioning sensors, and overloaded engines are not just about machines. They are about human judgment under pressure, about how in the roar of acceleration, small errors grow into irreversible chains. Every cockpit voice recording tells the same quiet truth. Danger doesn't always shout. Sometimes it whispers through habit, fatigue, or overconfidence. Modern aviation has learned from every one of these moments. Runway length monitoring, advanced takeoff configuration warnings, better brake performance, and automated surface awareness systems now protect flights worldwide. Each lesson was written in data, in metal, and in loss, yet each one reshaped the safety culture that defines air travel today. For pilots, the end of the runway is more than asphalt. It is a symbol of discipline. It reminds them that the sky rewards preparation, not chance. For the rest of us, it's a reminder that progress never comes without humility, that even the most advanced systems depend on the human hands guiding them. Every checklist, every briefing, every recalculation before takeoff exists because of the stories told in this film. They remind us that in aviation, perfection is not the goal, vigilance is. Because when there's no more runway, there is only what you did to be ready. If you found this story meaningful, subscribe and support the channel. Each new video helps preserve the lessons that were paid for dearly, so that every flight today can begin with more knowledge, more respect, and more awareness than the one before. Because every takeoff is still a test of precision, of trust, and of everything we've learned from the ones who didn't have enough runway left.